but in the, suppose you have a curve like this. So in a plane curve, it is very easy. Like I have a tangent here, right? And I know this is the normal, because this normal is also along the curvature. This is a circle of curvature, correct?
Yes.
So this will be along, maybe the bad, right? But this is the normal direction also. We basically will draw the outward normal, but you can also do the inward normal and so on. So this is the tangent and normal in a plane curve. Okay, if you have a space curve, it gets little bit complicated, like a helix. Okay, then you will have a tangent. Let's say this is the tangent. Then there will be a plane perpendicular to the tangent. Let's say this is the plane that is perpendicular to the tangent. So whatever lies on the plane is actually a potential normal. Okay, let me try to draw here. Isn't it? So if I draw
Sir,
a curve,
that is clear. That is clear. That normal is clear.
so in this case, no, it may not be very clear. In this case, there are several normals, out of which there is only one normal that passes through the circle, the center of circle of that curvature. So that normal is actually called as the principal normal.
Okay.
So this is in the case of a curve. Okay, now in the surface, okay, now if you take a Tn and B, T cross N, then this is the binormal. Okay, that is Tn and B on a curve. Now if you go to surface, okay, it is little, it's pretty much similar one only. Now here if you take any surface, okay, you have a point. So let's say you have one parametric curve here, another parametric curve here, and then this is the direction of tangent in this u direction. This is the direction of tangent in the v direction. Now if you take the cross product, you will get the normal at that point. Is it okay?
Yes.
Okay, this is at a, okay, let me just, so this is the normal at that, blue color one is the normal at that point on the surface. Okay.
Yes, sir.
So now this is clear, right? Now every
Yes, sir.
point on the surface will have a normal from the the tangent vectors in the parametric direction. Okay, now we'll go to the other picture. Okay, now this is the picture. Now for this parametric curve, you see this is u direction, let us say, and this is the w or w direction. Now based on this, you have a normal, correct? Which is, if you have p of u comma w, then you know p of u comma w, and then p w of u comma w. So this is one and this is the other. Okay, now if you rotate this plane, so now this plane is some direction. So this is one of the intersecting curves. Okay, now this guy will have a curvature. Correct?
Yes.
Okay, now you rotate this plane. Now if you keep on rotating this plane, you may get several curves like this based on the intersections. Correct?
So wouldn't
Yes.
you get like a continuous surface if you keep rotating?
No, if you keep rotating, you will get a set of curves at each point on a plane, let us say. I mean, of course, yes, if you keep on continuing, that could continue, but we only are interested in the intersection between the plane and the surface at that particular instance. Of course, you will get infinite number of curves potentially, and that will form a surface is what you are thinking. It is, we only look at the curves from these intersections. So each curve will have a curvature on its own, correct?
Yes, sir.
Yes.
This curvature, when you take the maximal and minimal of these curvatures, then you get what are called as the principal curvatures. This is very important concept in surface. So K1 and K2. So these principal curvatures locally will determine how the surface is. So there is a Gaussian curvature, which is K1 dot K2, and then there is a mean curvature, which is K1 plus K2 by 2. Okay, for example, you take that cylindrical surface, correct? We saw the cylindrical surface, correct? So what are the principal curvatures of this surface?
The circular part is like having, that is one curvature, and
Correct.
then the flat part.
Yes, and the other one is flat part. So your one curvature is from the circle of curvature, which will be the radius inverse of your radius of curvature, radius at that point. And then the other one is straight line, which is curvature 0. So you can see that K1 equals 1 by R and K2 is 0. So you can see in a very straightforward way, you can see that the principal curvatures here, you can see from one comes from circle, another comes from straight line. So of course, this is not the same as in other generic surfaces, but I am giving an example on that. So using this, you can determine, for example, if the Gaussian curvature is locally 0, then that means the curvature is, the surface is flat locally on that. So there are lots of properties which maybe we don't want to go too much into the details on it. I think I'll just possibly stop this session with this slide, because you have to understand the principal curvature. I think that is one of the important concepts. Hopefully they may use this in the further talks that you may, probably it may come on tomorrow or day after, when they talk more on the others. They are using kernel, I think, AC's kernel, but they said they're talking about the surfaces also there. So maybe this is going to be useful. There are first fundamental, second fundamental. I'm going to maybe skip that on. Okay, maybe I'll stop this maybe as a last slide. So you guys have any comments, questions? A lot of things went in today, I guess. I don't know whether all of you were able to assimilate everything on this.
Sir, when it comes to a two-dimensional curve, we can find out the curvature at a point by taking the inverse of the radius.
Correct.
But if it comes to a three-dimensional curve, at a point should we take like the sphere at
No,
the
no,
point and then find the radius of the sphere?
space curve, that is still a circle, but except that you have to take the alpha double dash. So if you go a little bit deep, you can show that alpha dash and alpha double dash are orthogonal to each other. Okay, you will see this dot product becoming 0. So whichever the direction perpendicularity to be, that will become the principal normal. Okay, so whichever that alpha double dash comes into, that one will be considered as the same as your normal direction. Okay, so this
Sir,
in the plane case, it is very simple. So
this
in
is like
the
the tangential velocity and centripetal
yeah, you have to
acceleration.
take your neighborhood, increase in the tangent, and then based on that, you find the alpha double dash. Basically, you find the second derivative of the curve. Suppose if you have an okay, we are using p of t. So if you are using p of t, then it is p dash of t and p double dash of t at that locality. So based on these three, you can see this p double dash of t in the three-dimensional one. It will actually coincide with the principal normal on that, and this is what this constant basically becomes the curvature at that point. So in 3D, you have to go for a particular direction in which this is along the principle, along this circle of curvature. So in 3D also, as far as I know, it is only the circle. We don't take a sphere there.
Sir,
We can imagine the helix. Okay, so imagine the
okay.
helix and take a point on the helix. So you can imagine that there will be some circle that is fitting at a point on the helix. Okay, which is along the plane of like the normal. Okay, that is the principal normal. Okay, that is where you can see the curvature aligning with your double derivative on it. So then that is the direction that you have to look at for your normal. Okay, so in the space curve, it is little tricky. Yeah, as you said. But you look at the helix, then it may be a little bit easier to understand from helix.
Thank you, sir.
Okay, other guys, I think there are only very few guys were interacting. So hopefully other guys also got something out of it. So any other questions?
Sir, okay, you just mentioned something about Gaussian curvature. So that was just the dot product of
Yeah,
the
it is
two.
dot product. It is basically K1 dot K2. We say K1, K2 are basically the values essentially. So they are not vectors, right? K1 is the principal curvature value, you can say, because K1 we saw as 1 by R, right? And then K2 was 0. So the dot product, basically this is not even dot product. So multiplication of these two kind of magnitudes of those vectors, we take it and then use K1 dot K2. That is not a dot product. Actually, it is only a multiplication. Like it's K1, K2 are normal values, not thing. And then Gaussian curvature, we use the term capital K. I shouldn't have used G. So capital K is just the product of the maximal and minimal principal curvature. Basically, they are values. It's a scalar quantity on.
Okay. No, I just looked up developable surfaces you had asked in the middle. So there it was given that if the Gaussian curvature is 0, then the
Correct.
surface is developable.
Correct. So yeah, so you can see that, for example, okay, the other question would be, are all ruled surfaces are developable, or all
Okay.
developable surfaces are ruled? Which is the
The
correct?
I cannot conceptually answer it, but the article gives the answer that in 3D they are like some of them are ruled, meaning it's not necessary that if it is developable, it needs to be ruled.
Okay.
However, in in 4D it is not necessary, but in 3D it is necessary. Something of that sort was given.
Okay. Yeah, I mean, I'm also not sure, but maybe currently I don't know how to imagine in other dimension. But yeah, so this is also an interesting question, and you can answer that via the Gaussian curvature. I mean, that's the whole point of that. So, but you have to come up with the correct answer. Whichever way it's correct, I think you have to give some reasoning. True. I mean, you can do that. Any other questions? I think we had a very long session today, I suppose.
Yes, sir.
So all of you still have energy, or nobody has energy left?
Sir, in the morning, did you mention something about Voronoi diagram or something?
Correct. I did, yeah.
Okay.
Like, you are not going to see this in this class. So
Okay. No. In general, I just was asking
yeah.
because
Warnock diagrams. See, Warnock diagrams is usually we start with points. It's a very popular one in computational geometry. Okay. But it has been extended to lines, curves, surfaces. In curves and surfaces, it is going to be Warnock diagram is since you asked, that is my pet subject. So since you asked, I have to at least tell something on that. So it is very simple concept actually. So you take 3 points on plane. Let's say you take 3 points. Okay, let's say first you leave that. Let's say you take 2 points. Let's say imagine that I go to a new thing. That will be very interesting. So if you take this entire page, okay, suppose if you have 2 points here, okay, let's say you have 2 points. Now, if I want to divide this space, so what is the possible way in which you can divide this space?
as in just we break it into two parts, as in
Whatever,
one
two
half will
parts.
contain.
Okay. So one way is that you take the perpendicular bisector of these two guys, right?
Yes.
Then this is one space, and so you can see that whatever you have here, a point, let's say P, let's say if you mark P1 and P2, so P2 will be the closest. Okay. And then if you take any point on this side, you can clearly see P1 will be the closest. So basically, Voronoi diagram subdivides the space into regions, which will address your closest query better on that. So if you have if you have 3 points, what will happen? That will be interesting. So if you have 3 points like this, the Voronoi diagram will be pairs of things. So you can see this will be the Voronoi diagram. So if you have P1, P2, P3, each one will have its own Voronoi region. So this is Voronoi region of what is? So this is Voronoi region of P1. So this side, if you are on this side, any point that you take, P1 will be the closest. So if you take any point here, P3 will be the closest. So if you take any point here, then P2 will be the closest. Basically,
Like
it subdivides subdivides regions into set of, subdivides the plane into set of regions, where if you take any query point, that corresponding point will be the shortest. That is, this is called shortest path Voronoi diagram. There are farthest point Voronoi diagram also, and there are different metrics in which Voronoi diagram can be done. So it is if you do it for any number of points, I can draw it because I'm quite familiar with that. So if you take 10 n point number of points, okay, if you have 1 point, so you can draw the Voronoi diagram. This will be like this.
Sir, but how exactly do you draw it? Like is it intuition or some mathematical?
Mathematically, it is basically a set of intersection of half spaces, what are called half spaces. Like if you have 2 points, you remember this is one half and this is the other half. So this line is basically called as a half space. Okay. So basically, this will be the set of intersections of half spaces, if you can think of, or half lines, whatever. So then it will come out to the Voronoi diagram on that. Basically, this is the Voronoi diagram. Each one will have what is called as a Voronoi region. Region means whenever you are in this region, then that will be the closest guy. So this is the shortest path Voronoi diagram. So we have lots of algorithms on that, but you can imagine this extending to curves and surfaces and so on. This will be a little tricky. For example, if I ask you a question like, what is the Voronoi region, Voronoi diagram between two circles? Let's say one circle is outside the other circle. So what will be your answer? Let's say there are two circles badly drawn. So then what is the Voronoi diagram for this?
Okay. Equidistant. equidistant for the whole circle, you are saying?
Equidistant from both circles. Need not be of same radii. Okay, the circle could be different radii.
Maybe divide it into
Okay.
3 parts.
We will still divide only into 2 parts, but it can be different from one to depending on where it is located. The shape may be little different probably. So will it be a straight line? Need not be. So if there are 2 circles of let's say same radii, then you can see that this will be the Warnock diagram because this will be equidistant from both sides of equal radius. So now that may not be true when you have a circle of different radii. So what will be the shape then? So it will be little difficult on that. So what will be the shape of here? So it actually could go to hyperbola kind of.
Okay.
Okay, there are proofs on that. Okay, there are different shapes, and if you have a circle inside another circle, it is not exactly concentric, then the bisector will be ellipse on that. There are lots of proofs on that. So the Warnock diagram will be built on ellipses. So this is a little bit tricky as you go more and more. Warnock diagram can become very complex at some point. So if you can imagine Warnock diagram for 2 B-spline surfaces or B-spline curves.
Okay.
I think I become silent now, but it's okay.
Sir, here circle inside a circle will consider as a cavity.
Now, the region of interest is between those 2 circles, kind of. So you will have an equidistant one. Like for example, if you take any point on this one, this is equidistant to this point. Basically, if you take a bisector, right, it's equidistant, correct? So basically, you are trying to find equidistant, which means in terms of other terminology, it is bisector, but bisector is not all. It will be only a subset of bisector. Then a lot of things I have to explain. So maybe we will leave it on that. Yes, it has a lot of relation to bisector, and in this case, it becomes like an ellipse between 2 circles on that, which are of different radii. Same radii will have, if you have concentric circle, right, 2 concentric circles, then you see the bisector is also a circle. So the cases will differ depending on the location and position and radii of the circles and so on. Geometry will play a great role.
But here parabola will be the case of a point to a line like.
Correct. Fantastic. Yes. Correct. So between a point, but there are 2 cases. Okay, it will be interesting. One case is that if you have a line here and you have a point, it is a parabola. Okay. Now the other case could be I have a line here, and suppose if this point is here, what is the bisector?
For line and line, it will be a line.
Line and a point, where the point is lying here. So in the previous case, the point is, in this case, you have point and line are distinct. Where in this case, I am telling a point and a line where the point is lying on the line. So what will be bisector of these 2 cases?
Sir, is it the point itself?
No, but then you compute the distance. Are they going to be equidistant? So it has to be equidistant from both, right?
Okay, it won't be equidistant.
It won't be equidistant from both, correct?
Okay, is it a circle in the plane, like around the point, like making the line as a normal?
Okay. So basically, it will be a normal to the line on that point. That is the bisector. So if you take any point here, so the distance between the line and the point are equal. So the bisector basically will be a perpendicular line passing through that point. Of course, you can extend here also.
Okay, in 2D it is a perpendicular. Okay.
Yeah, 2D. Yeah. I mean, if you go to 3D and other things, it can become quite complicated. I mean, it's a very interesting topic. I can talk hours and hours on that, but in the interest of all participants, maybe, if you want to talk to me later, we can talk on off the line. We'll take it up. No problem.
Yes.
Okay. So I think hopefully I have given some glimpse of Bezier and B-spline curves and surfaces today. So I would probably like to stop. I mean, maybe Aditya there?
Yes, yes. Yeah. Thanks a lot for a very intuitive and interactive session. Basically, introduce geometry, which is what the rest of the course would rely on. So, thanks
Okay.
a lot.
Okay. So hopefully all the participants, many of them did not speak even a single word. I'm very unfortunate. So hopefully you will also interact more with the other people, and see, the whole idea of the workshop is that you guys have to interact with us and learn the subject more, and hopefully go for research. And I really like this in discussions on Warnock diagram. I mean, I would talk more, but I don't know whether all the guys are interested. So because I'm not getting any feedback, so it is unfortunate. So I can talk more and more and more, but it may not make sense for a lot of other guys. And I think we are also tired after some 5 hours plus or something like that. It may make sense to stop than continue.
So next Friday, anyways, once the sort of school.
Yeah, but if you want, guys, we can talk about what are the geometry research problems that we typically do in curves and surfaces. I think all other guys are going to talk more of. I think Aditya and now yesterday we saw Saturday. They are more of point sets, mesh, right? Mesh model. I think Laplace Beltrami also going to happen on mesh model, and I think
Yes.
Geometric deep learning also, like graph based, also may happen on mesh model or a point set. I mean, I do work a lot of point set, but if you want something to give me extra hints on curves and surfaces, I'll be more than happy to do that also. I mean, it depends on you guys and whether the participants are willing to spend. I'm okay with that.
Right.
Maybe
So
get a feedback if you want an hour of 30 minutes to 1 hour of some brainstorming session on various geometry problems that we do on curves and surfaces. I'm more than happy to get in something on that. I don't have a problem.
right. So next Friday, we have a sort of a panel discussion where we try to give participants our own view on what opportunities are there, maybe for research or industry. So I think all of us would be happy to hear from you.
Sure. I can prepare a small presentation, or I can show demo. Demo is there. I mean, unfortunately, not many people know about this ERIT. I think this is fantastic open source one that he has done. It's completely free. I mean, if you want to compute surface intersection, even he has created VREPs called as volumetric reps. If you know VREP, which is a higher version of VREP, he came up with the volume VREP and so on. It's really fantastic. I think unfortunately not many people know about that. So
how about Blender?
Hmm?
How about Blender?
No.
That is
Blender.
No. This is entirely. This is based on numerical solving
Oh,
approach.
okay.
So this is not a commercial one.
Right.
I mean, what is done is not a commercial one. But I think it may be able to do more than commercial versions actually.
Okay.
In fact, I'm very thankful to you. I was not knowing about this particular software. In fact, it's very useful. Any amount of hand waving that you do in the class, you cannot communicate the concept unless you give demonstration.
Correct. Actually, the Windows version of this works much better. Unfortunately, I kind of have all Macs in my thing, and I have been telling him because he is more of, it's more of Windows guy and kind of a thing. So he, after a lot of thing, he put a Mac version, I think, but some problems are always there. Even in ERIT, when I work on that, I'll have some issues on that. But if you work on this Windows version, you can really, and I would recommend it to look at that YouTube video, which is very short. It's only 15 minutes.
I had a quick look at the YouTube video, and also I installed it. It's running fine. I mean, except that I'm not yet useful. I'm not very familiar with the user interface. It's how to input the points, etc. With the click of a mouse. It's not happening. I mean, I'll figure it out.
I would say
but it's very useful, particularly for educational purpose. Because B spline, B surfaces. I mean, particularly CSG, for example, right?
Yes.
Yeah. So Blender is more for those who want to design something and artistically. It doesn't have the kind of control that this seems to have. The number of primitives, etc.
Quite true. I mean, actually, this thought came to me yesterday only. In fact, this because I was thinking how to demonstrate, and suddenly I remember, because I am also not working too much in curves and surfaces nowadays. I should admit that. There are only very few guys in my PhD work on, maybe one. So I kind of a little bit forgot this. Suddenly it struck me that we had this tool, and why not use this? Okay, so the moment I realized that, then I sent a message to Aditya and asked other participants to install. And me also, I'm a little bit out of touch with that to catch up with that. But Windows version, if you use it, it will be really great. You can learn a lot from this tool, I would say, really. To me, it suddenly struck this, and I thought I should use this. But I was trying in various of my Mac machines, and my became a flop show in this so-called big density machines like your new Retina display. It became a complete show. So I think what I understood is that instead of pixels converted to points in the Retina display, and that maps all the things to only 1/4 of your resolution after
I
that.
see.
So that is why everything becomes in one corner. I was so disappointed to see this one corner thing in my laptop yesterday. But I didn't know what to do because I know that my Mac is little slow, and that's why I had a plan B today too. And it was really great that we could use both machines actually. It's more accident, I would say. No plan in that. Okay, so I think hope all had some glimpse of this. So if nothing, then we will leave and people try out. I should say all people should try out GUID and understand the curves and surfaces better. That is what I would say. Finally.
Sir, I find some segmentation related stuffs in your
Yeah.
website.
True.
So basically, what are the kind of work currently you are doing for the latest modes of research, which is not purely this modeling based in terms of
This modeling, I mean, technically for practical purpose, I mean, I don't think others want to do curves and surface, so I kind of barge in. Practically speaking, I mean, that's also good. I also really enjoy that. But currently, I work more on mesh model and point set processing, and more towards also segmentation and feature identification. Feature identification, not in terms of typical point set, guys, where they try to, let's say you have a finger and they try to feature points like the top of finger, but we typically work on some mechanical feature extraction like your hole slots. So in a point set, it's difficult to figure out what's happening there. So, and also we do a lot on segmentation. We also currently looking at segmentation using deep learning. I'm also handling a course in machine learning. So this is a kind of a course which I'm not doing too much on that, unfortunately, although I would love to do it. But we do mostly on segmentation, search problem, like what do you do it in Google search with images, or we do on 3D model search. Okay, we do give a 3D model as an input and then try to get different 3D models that are similar. So we also do that's called as a shape search problem. So all problems in mesh and other things we are actually focusing on via some of the newer approaches, including deep learning, and of course algorithms also we are working, like all the Warner diagram, medial axis, shortest path, all the algorithms also we are working on. So we are working on one in algorithmic direction, another in the, I would say in the learning based approach direction. Okay, that way, either way it's fine. If you are segmenting via algorithm or segmenting via deep learning, I mean, we could go in either direction. So this is unfortunately, see, there are lots of classical problems in this geometry field of curves and surfaces, which are not very easy. For example, even Warner diagram is not an easy problem to solve for curves and surfaces. Okay, not at all easy. I mean, okay, I can show you one simple case of what will happen. What will happen to a bisector curve? Like for example, if you take a curve like this, okay. So if you take a curve and a point, so the bisector can be something like this. Something like this. So if you take a curve, one curve and the other thing, the bisector actually, the behavior of the bisector will be like this. So this will be the bisector, which is I don't think any of us can come up with the shape of a bisector like this for two curves. This is curve 1 and curve 2, and this is the bisector between these two curves. I mean, so it's actually very complex problem, both numerically and I would say on the algorithm side also, but very interesting. We have solved such problems actually. I mean, I was working with Gershon on my postdoc during that term. Actually, that is the term I actually got to know about IRID, and I worked on IRID, so I have some experience on that. Otherwise, even before, I didn't know much about that, unfortunately. So such problems are there, and you can do this for surfaces. Even take the cases of spheres, okay, very complex. Okay, just take the case of two spheres, try to understand bisector. It can be hyperboloid of two sheets, okay, like what we saw as a hyperbolic paraboloid. Okay, it can be something similar to that, but it's more of hyperboloid of two sheets. And how do you handle that? I mean, numerically, it's a very intricate one on that. And we have devised some methods for that. We are working on Warner diagram of spheres also recently. But we are actually developing something on Warner diagram of circles, but using very minimal number of computations on that. So all the things we are doing actually on algorithms also we are doing. So yes, if you go to my homepage, you get all those details. I'd be more interested if you contact me later. We can have separate sessions also. Who asked this question?
Soma.
Okay, Soman. Okay, so you can mail me later. We can have this. What are you doing currently?
Sir, currently I'm pursuing my master's from IIIT Delhi in
What branch?
computer science. My specialization is in AI.
Okay. I mean, we don't do Warner diagrams with AI. I think I don't know how to do that, honestly. So, AI, we are almost, in my opinion, we are kind of brown beating for everything. But I don't know, suppose if you are given two Warner diagrams for two sets of points, I don't know whether it can automatically figure out what should be the Warner diagram for another set of points. I don't know. I mean, actually, we are going to try not on Warner diagram, but some other related problem. If you know art gallery problem, we are actually going to try that. We are actually started trying that using deep learning.
Sir, is it like a lot of motion planning people I found in using Voronoi diagram?
Yes, correct. All robotics guys use that. See, basically, if you have obstacles, right, and if you have a robot of reasonable size, the idea is that if you move your robot along with the Voronoi diagram, then that will be an obstacle free. Like for example, it's simple, right? If I have two and this is the bisector, terribly drawn. But if you see a robot here, and if this robot moves along this bisector up to a certain size, you see that it will go obstacle free, right? So
Yes.
that is the reason why Warner diagrams are being used quite a lot in motion planning.
Yes.
But they may use more of discrete Warner diagram computation, which is sufficient. I mean, you don't have to use these continuous curves. As you see, this is a really headache. Okay. So a discrete Warner diagram actually will actually do much better there. And they actually resort to that.
Yes.
Yeah, nice.
I am actually in control, so that's why I got.
Sure.
Immediately caught that Voronoi diagram thing.
Voronoi, see, there are two guys. One is the Voronoi diagram. Okay, I'll quickly tell the other guy, which is really fascinating. Okay.
Is it Delaunay?
Delaunay triangulation. Absolutely fantastic, guys. Okay. Let me tell you, this is the Voronoi diagram of, let's say I'll just draw quickly. So if you draw quickly, then this is the Voronoi diagram. Okay. So this will be the Warner diagram of this set of points. Okay, so if you take the dual of this, which means that whenever there is a Warner edge, I will connect this dual graph. Okay, I will connect the 2 points. Okay, like this, and there is a Warner edge between these two. I will connect this. Okay, and there is a Warner edge here. I will connect these two, and then I will connect these two and connect these two, and you can see that this becomes what? This is a what? This is a set of triangles. You don't connect this point and this point because they don't share a Warner edge. So this is called as a Delaunay triangulation, which is basically a dual of Warner. Okay, or you can consider Warner of Delaunay or whatever. So these two structures are amazing. Okay, even more than Warner. I have used Delaunay for anything and everything, so to speak. Almost we have done some 10-15 algorithms on reconstruction itself based on Delaunay triangulation. Very fascinating structure. And there is one more guy called as alpha shape, which comes from Delaunay triangulation. I mean, these structures are just so beautiful. I mean, I tell you, we can say that imagine where all they can be used. Superb, guys. I mean, it's just impossible to mention the applications, number of applications that they have in the real world. It's just too many. And it's just that we have not explored enough, I would say. So beautiful stuff. Yeah. So you can use Voronoi, Delaunay, all those things on that. It's fascinating structure. It is very good in 3D also. And we have used this extensively both in 2D reconstruction as well as in 3D reconstruction. I mean, it has been effective, excellent. I can't really thank the Delaney for running my research, I would say. Half of the paper
Even discrete form is there for this Delaney and.
What do you mean? This is a triangulation only. It's a discrete form only in that sense.
Okay.
So, but the continuous form is difficult if you are talking about it. For example, if you instead of replace this set of points by set of circles, okay, Varna is defined, whereas Delaney will go for a toss. Okay. I mean, Delaney also conceptually can do, but I don't know whether it will exactly replicate what you have for a point set. Though we have also defined it, but it's pretty good. I mean, all Delaney alpha you can the definition wise will remain, but how you use in practice will vary from input set to another input set. But these are all classical structures. I mean, I would honestly tell you should get to know. And this is also another problem, like this computational geometry field is also not very well known in our country. Isn't it so? I don't know about other guys, Aditya.
Not many people.
Not many people, I think. So, but these are all fascinating structures. And there, I would say, you can't even imagine I have used this Delaney triangulation to solve some GPS customer service problem or customer preference problem based on Delaney. It will look very funny. These guys are absolutely amazing, and you people should get to know about Voronoi, Delaney triangulation, and so on. I think there is a session somewhere tomorrow, right? Somebody is going to handle Voronoi and Delaney.
I hope so. Let's see. Tomorrow afternoon, we just going to talk about discrete surfaces.
Okay. I think I saw that they are planning to talk on Voronoi, right? If I
most likely it should be just.
Yeah. So I think you guys should probably ask some questions and see, how we can benefit from such structure. Honestly, I ask you to read about Voronoi, Delaney a lot. There are very good books. One by Joseph Woru, if you know Woru. He is kind of the grandfather of computation geometry, pretty much. He's also probably now 70 or something. Fascinating guy. There is an open book. I think you should also read another book which is available on the web. That's called as Art Gallery Theorem book. Okay, you guys should read this book.
Art Gallery Theorem. Just.
So this book he has put in his web page itself on that. Okay, this only gives a very very minuscule of what this entire set. There's a book on this problem, but he can probably write another 2 books on this problem. I'm talking about one problem. Okay, this is Art Gallery problem. And I am sure that we can write another couple of books on this. There's so much of material, may not be out there with everybody. If you collect it, we have done a lot of work on this problem. It's also a fascinating problem.
Yes.
So anything else, guys? I think shall we wrap up this? If you don't have, I have a meeting at 4:30 also.
Oh.
So guys, any
Yeah, thanks a lot once again.
Sure.
Hope to see you next Friday.
Sure. Just send an email reminder, and hopefully you guys benefited from our discussion today. And
I'm sure. I did.
That is the whole idea. And I would have liked little bit more interaction from the participants. Okay, I think of course I know that many are not forthcoming, but I would have loved more discussion. I mean, these discussions I really love it. All these problems and so on. Okay, so see you guys. I think we'll meet again next Friday. Okay, see you then. Bye.